Hello and welcome back to another festive coding session with Mr. Jacob. Today again as usual, with my trusty Grinch mug here, we are going to tackle the advent of languages, day 7 to be precise. Yesterday we did logo, the language logo. Today we are going to do something in the language Go. So what we are trying to do here is we are trying to implement on each day of the Advent, so from the 1st of December to the 24th of December, implement each day the same program logic in a different language. And what we essentially striving to do is output something that looks kind of like this ASCII art tree here, which is then nicely rendered somehow using a different language. The last time we did this in Logo, which was a little bit different because it is a graphical turtle-based language, so we could actually draw there some kind of vector art. Today, we want to tackle the language Go. So let me quickly copy this tree here because we will use it as a reference later on. And now let's go ahead and start. So let's make and cd directly into this folder 07 Golang and start with a clean slate there, so that we can now go to something like go mod init and then hello Xmas. And now we should be able to do something like main go, edit the main go file, and let's put our Christmas tree in here, I guess, just to have a reference. Let's comment this thing and let's clean up the spacing a little. So just that we have something to actually reason about when implementing this, like we always do here. And we now need to specify that this is the main package of our application, so that Go knows, this is the entry point actually, and not some library module or something like that. What we need to do now is, first of all, we need some sort of main function here. And we define that in Go by simply using the func keyword. And then we could do something like, for example, use the fmt package, which we will anyways use to format our stuff, and do some format printf here and start with hello Xmas, just to see that we have a running program here. I'm not even sure if I need a semicolon here at the end. We will see, I guess. So this should already maybe work. Let's see. No, I don't. I think I need to import FMT, don't I? So let's import the FMT package, and now this should actually hopefully do. So let's save it and let's do go run and give it the file there, and it should compile and it tells us hello Xmas. So this works. That's already quite nice. And essentially what this formatting thingy here does is it is a module here which we can import, or a package. I think that's the Go term for it. I'm usually not using Go, but I think the Go term for it is package. And we are using the printf function exposed from this package here. And essentially this printf implementation is a Go implementation of mainly the printf functionality that actually the C standard library gets us, or the C standard IO, better said, gets us there as well. So we can do we can actually do formatting things, like we could do something like put a placeholder here, which should be a string, and then put this Xmas here in the end. And then if we run and compile this, it works exactly the same way. We can do some more interesting things, like named placeholders based on interfaces, more or less objects that we can put in there, and then have that. So structs, we can put a struct in there instead and use then named referencing. We can use positional referencing and all that kind of stuff. I'm not sure that we're actually going to use that. However, we could if you want to. If we are going to use that, then I will explain it to you when we do. So all in all, the printf implementation is quite powerful in Go. So let's see, how would we continue here? As always, I guess we should implement something that will draw this. However, I thought maybe we now have again a language that understands and can handle structs and the corresponding interfaces based on that. And that is actually something that Go has a special way of handling, like interfaces are implemented on structs, that I thought I might demonstrate this in this video when we are doing this anyway. So I thought we might start by simply defining a new type for us, which we call tree, or we could call it Xmas tree or X tree or something. Let's just call it tree. And this is actually a struct. And this will contain certain information that we can then use and build up to output our tree, actually. So I think what we need here is something like, for example, lines, where we can internally store our created tree lines while we are creating it, because we are creating it part by part by part before then in the end outputting that. That would be a nice thing. So I guess this should be a string array slice. So this is actually a string array, so an array, of strings. And you define it that way in Go, where you always have the more or less the thing that you want define the type of, followed by the type. And in this specific situation, we want to define as a type actually of lines, we want to define an array there, and we want to define an array of strings. So that is actually how you put that together. It's a little bit confusing at first, but you get used to that very, very shortly. Then once we have the lines, I guess we need something like the depth, the amount, so to speak, the length of the tree. So we usually call that len. Len is a reserved keyword in Go, so I guess we will call that simply length, and length will be an integer, where we can actually then store our length. Okay, now we have this struct. How would we actually create this struct? That would be kind of interesting, I guess, because there is no specific way in Go to create a struct. The usual thing is to just put a factory kind of constructor or factory function with a new name into your package, or a new followed by the name of the struct into your package, and expose that and use that. So I guess we simply do that and call that new tree. And the only thing that this thing needs to know actually is the length. So we can actually give it that length. And now we can implement the new tree function. And what should the new tree function return? Yeah, by default usually, or by convention, or however you might say that, you are usually returning a pointer to our tree type there. And that's exactly what we are going to do. We are telling the system that we want a pointer to our new tree, which we simply create using this syntax. And the ones of you who following my Rust videos usually might know this syntax, or it might look quite familiar because it's more or less the same syntax with this curly braces. So what we now do is we simply define our object contents here. So we put into the lines object, we want to import or put an empty string array in there first. So how we do that is with this syntax, which simply creates an empty string array, literal kind of. So you would normally put your stuff in here. However, as we don't have content and want that empty, we could do it like that, or we could do it like using the make function. There is something like you have make, and then you put the type in there, for example, like this, and then the element size, and this would work exactly the same. However, I kind of prefer this syntax. It's just as you like it. Okay, so now that we have the lines, we need the length. We simply take the length from our input there and put that in there, and now we should actually have a new tree function. So let's try and create a new tree. So actually defining variables or setting values, you are doing with this colon equal syntax in Go. And so we can now simply call new tree, and we give it a length, I don't know, 7 maybe. And now we should actually still be able to compile this if we didn't make something wrong there. And we actually did something wrong there. Syntax error, unexpected colon, expected type. Okay, where exactly are we? In line 17. Let's see what we did wrong there. Something we made wrong there. What I can definitely see directly is that I'm missing a comma here, because actually Go is enforcing some things in its syntax, like for example dangling commas. Dangling commas are enforced by the compiler, which is kind of an interesting thing. I missed that there, so I had to add it there, and I need to add that there as well. However, I'm not 100% sure why this is not working. It tells me that, wait a second, let me do that again. It tells me that the colon is unexpected, but it is actually expecting a type. Was the struct type definition done like this? Now I'm not 100% sure. Might be. Yeah, even looks a lot better to me now. So syntax error, unexpected comma in struct type, possibly missing a semicolon or new line. Okay, I guess we are defining types then like this. Declared and not used tree. Okay, I'm kind of fine with that. So it seems now to compile. So now how would we actually call something on the tree or define a function on our tree? And that is actually the interesting part, because in order to implement something, for example, for an interface or for no to first of all, to implement a function on something like the new tree, the tree object here, we simply do have this syntax where we tell it that we want a context of this object, actually, which we then name like we want. So we tell it that we want the context of this tree here, and this should actually be a pointer to the tree. And then we are defining a function on that one. That could, for example, be something like string, to convert it into a string, actually. Something like this, yeah? And now that means that, first of all, we have access to tree here. We can now use this pointer here and access, therefore, our tree struct, where this function now is called upon so that we can access it. Furthermore, you might be wondering why it is kind of strange that all these functions start with a capital letter. In Go, it is actually the coding style that everything that will be publicly exposed on a module or on a struct or anywhere is actually starting with a big letter. So even kind of method names, if you could call them like that, are exposed using capital symbols. So that's just the way it is. Okay, so I will get to this implementation here in a second. So what we could now do here is, for example, instead of now doing all of the stuff like creating our tree and returning it, we just could do something like foobar here for now, yeah? Or we call this tree, something like that. And now we would essentially be able to create this tree, and then instead of printing the tree here, we could actually, or printing this hello Xmas, we should be able to print the tree. I'm not 100% sure if this is auto-converted or if I need to do that. Okay, it's not auto-converted, so I guess I need to either cast this into a string. No, this does not work as well. I'm not 100% sure anymore how I cast in Go, actually. But what I definitely can do is I can do it like this. I can say, okay, put a string in there, and then I put a tree in there, and then it will definitely call the string function. And now is the question, why did it call the string function? How did it know that it actually can convert this object into string? Is that some sort of formality that exists within Go? Exactly. What we did here by implementing the string function on our tree is we actually implemented the so-called stringer interface. So Go consists of a lot of interfaces. You can actually define your own if you want in your application. And what we did there is we implemented an interface for this tree struct. So you do not need to specifically give the information about implementing some sort of interface and then implementing methods like in other languages. You simply implement the functions on the corresponding struct that you need for a specific interface. And the moment you have this functions implemented, all of them that are needed by a specific interface, your new struct actually confines to this or conforms to this interface that you want to implement. And you can then use it in this way, in the way of this interface. So there are, for example, interfaces for I/O, for reading, for writing, and all of that kind of stuff. There are implementations or interfaces like this stringer interface, for example, which is defined by simply implementing a function called string, which returns a string. And that is exactly what we did there. And that is why we can use our object as a string. Okay, so now we have talked a little about all of this stuff. So let's get going and implement our tree here, I think. So I guess we call something now on our tree. So let's do tree, create, yeah, we called that always groups, didn't we? So we could create groups and this would actually be a nice way to do that. And as you can see now, this method or this function here now doesn't start with a capital letter because this thing is private to our struct. We are only using it internally and not exposing it to the outside world where it can be used. So yeah, I guess we then simply define this function here. On our tree, we do implement this create groups function here. And essentially this one does not return anything. And now we need to create our tree groups. So these thingies here though. So this one and this one and this one. And actually this is, as always, the same thing as we are creating them. We need a defined amount of spaces, then we need a slash, then we need another defined amount of spaces, we need a backslash, and then we are done for each of the lines. So what we actually want to do here is we want first of all append something to our already stored lines. And in Go, actually, you cannot, at least to my knowledge, that easily manipulate the innards of an array. You always need to do that in a in a way that creates a new array. So what we do here is we say we want tree lines to equal append, and then we give it actually where we want to append of what we want to append to, like tree lines. Then we give it the new element, which we will create in a second. And once we have done this, it will simply give us a new array there, a new array slice, which then contains the new element. And it will internally choose a nice way to do that, at least I hope. Okay, so now we actually want to append to our tree lines the first line of this created by the group. What we need to do, of course, is we need a loop here because we need to loop through our amount of groups here. So how do we do that in Rust, actually? In Go, actually, sorry. So we could either use the usual C style, like for I, where I starts at 0 and as long as it is less than, and so on and so on. Or we can do the ways that we know from other languages like Rust, for example, or Python or something like that. We can do something like for I is defined as a range from, and this is then actually, if you specify only one part, it's from 0 to exclusively, not inclusively, the given range. And this is exactly what we want. We want tree length. So we want to loop through this here, and we usually call it N, I think, in our other code there. We want to add tree lines for each of those groups there. And what we want to do actually is we now need spaces. The amount that we have there as space should actually be the amount of the tree length that we want to print, so the n, but the n subtracted from the full length. So at the top, we need kind of the maximum length of the tree in spaces because we need the first area to be centered. So if you look at that, we need the most spaces here, and then they get less and less and less. And that is exactly what we are going to implement now. And we are going actually to implement it more or less the same way than we did with our C example using the printf formatting tricks that we used there. So what we actually can do is here, we can use printf to actually create a couple of spaces because we can define the width of a string there. So what we can do is we specify with a star that we want, instead of giving it a number directly, use a positional argument here for that, and then we want a string. And what we essentially do here is we tell it that we want the tree dot length minus n amount, there in spaces, and we need to add 1 actually because we are doing the width, and we want the width of this one character that we are specifying here now. We want that to be the amount of spaces plus its own character. That's why we are doing +1, and then it will be padded kind of in the exact way that we want. And we are doing the same thing then again here. So we are saying we are doing that exact same thing again before actually adding a new line. Or no, maybe we don't want a new line. We don't even want printf actually, because we don't want to print that. We want an sprintf, but I think sprintf exists. I'm not 100% sure if it's sprintf with a big P or a lowercase p. We will see. But there is a string version of that, I'm quite sure. So we are doing the same trick here as well, and we are using no, not tree length, but now we need the spacing in between the characters, which would be actually n times 2 in this case. And we want n times 2 plus 1, of course, again, because we need to incorporate the last character there, which is a backspace there as well. So let's see if this already does what we want, because we need the line below that, which actually has kind of the same. However, it needs 1 less spacing in front, and it needs n plus 1 times 2 spacing in between. And if we do that, actually, I hope that we might already have created the basic tree shape that we need there. So let's go and see. We are creating this thing, and then we are outputting the string here, and tree is actually currently only creating groups. We need to somehow actually make this array that we now have here, those lines, into a single string. And that's actually where we use the string module, which of a package, which of course we need to import then as well. So is it? I guess it's strings. I'm not 100% sure, but I think it is the strings package, and it has something like concat. Or was it join? I'm not 100% sure. I think it is concat, and you give it the data here, the strings array there, and then we just tell it to do that with a new line, and that would hopefully do the right thing. Let's see if we now kind of get our right structure. So there is a problem in line 13, so we need to import it like this, and now we have unexpected new line in argument list, possibly missing comma, or where is that in line 33? So we have done something not correct here. So this should actually expect 2 arguments then. So 1, 2, and the other one should expect 2 arguments as well. So 1, 2, that is kind of strange. Let me quickly just add braces there to see how this actually, if this actually fixes it. No, unexpected new line in argument list. Wait, what? Where's a new line in the... I guess there's, it meant that this comma is missing. It's already again this, I can remove that again then. It's already again this enforcement of dangling commas if we split that. Okay, so undefined SMT fprintf and undefined strings concat. Okay, that's not good. Actually, let's see if this is if this is the name. Yes, okay, that is okay. That is what I wanted there. So now we are just having concat. Is it not concat? Is it maybe join? Is it really join? I'm not sure. Let's see. Okay, it was join. So now we have the basic structure of our tree. And now what we need to do, of course, is we need to create this this line here below. We can use exactly the same trick that we did before in C as well again. So we simply do an append on tree lines where we add a new string there, and we are using actually fmt sprintf there for the works. And what we do is we use the precision argument on strings. So what we are doing is we telling it, do make this string specified in the arguments precision, like it then cuts it until the width of this string is fit. You can use this for floating points and stuff like that, usually to have a certain amount of decimal points, but you can use it on strings as well, and it works. So what we are doing there is we are now specifying the length, and the length actually is the tree length times 2 plus 2. That is how many dashes we want. And we want dashes, and that's actually something that we can do here. We have this string as a dash, and now we simply put in there. I'm just realizing we could have used this anyways, so maybe we should, because there is a repeat function on strings, if I remember correctly. So I could do something like tree length times 2 plus 2. Can I actually do that? Let me quickly see if this compiles, because if this compiles, no, it does not. Undefined, okay, because I have append. I have a typo there. So what's the problem there? Is not used. Repeat undefined. Type untied string has no field or method repeat. Okay, then maybe I'm wrong. However, there is something, or is it strings repeat? There is a way to create a repeated string. I'm quite sure of that. However, what we can simply do is we can put a large string of minuses in here. That's exactly actually what we did in C before, and it doesn't work as well. Value of type string is not used. Oh yes, of course, because we need to do something like tree lines equals. That's the thing with the read-only variables there. And as you can see now, we have the correct line here because we kind of cut it from this really long line of minus characters. We cut it what we need there out in the length that we need. And the only thing that we now need still to do is we need to create the trunk. And once we have done that, let's define a function for that. Func on tree on a tree pointer there. We want that one, and it's called create trunk, and it will return nothing. And what it does is it goes ahead and appends to tree lines another formatted construct. So tree lines fmt sprintf, and what we are actually doing here is the same spacing trick as before. Again, we are doing an s with a certain spacing followed by a pipe. And then we are doing the spacing, which is actually tree.length exactly. And we are using one pipe character so that in the end we have actually 2 of them there. And now if we close this command here and we copy this thing there. We should actually, unexpected new line. I think I missed the comma there at the end again, the dangling one. And now we have our Christmas tree, and we, as always, can configure it by simply, for example, creating a Christmas tree of 9 gear, and we can run that and we have an even bigger Christmas tree. And that is it for our implementation of our Christmas tree within Go. If you want to play around with that, just check out the code in the repository link down below and maybe add ornaments to it or do some other experimentations with it. I hope you had fun seeing me implement our advent of languages Go kind of challenge here today. And I hope you had fun and enjoyed that. And I hope you give this video a like and a thumbs up. You may leave me a comment, hit the subscribe button if you want to be informed when a new video is out on this channel. And yeah, I hope to see you in the next one. So have a great day and bye.